wastewater treatment and the future of treatment. Jeff Spencer from BI Pure Water Canada Inc. is the technical sales lead at BI Pure. He's a leading designer and manufacturer of packaged water treatment plants in Canada with 25 years experience. BIPW has more packaged plants in the north of Canada than any other company. Jeff has significant experience with water treatment technologies over the last dozen years. So over to you, Jeff. He's presenting virtually.
Can you hear me all right? Okay, can everyone hear me all right? I'm going to assume so. So good afternoon. Thanks for having me. My name is Jeff Spencer. I work with BI Pure Water. BI Pure Water designs and builds water and wastewater treatment systems. When building our systems, BI Pure Water utilizes the best available technology to meet the water treatment objectives. Population and economic growth have increased the demand on our water resources. Today, more than 30% of the world's population lives in water-scarce regions. As cities continue to grow and climate change alters availability and distribution of water resources, it will become increasingly difficult as well as more energy intensive to meet the increased water demands. The increased demands from urban development requires approaches that minimize resource consumption and focus on resource recovery. Wastewater should be considered a valuable resource from which energy, nutrients, and water can be extracted. We need to think beyond the typical POD TSS reduction system. Today, I wanted to highlight some of the water treatment technologies available that could be incorporated to better improve the way we treat our water and wastewater. These technologies can support sustainability as well as assist with the destruction of difficult to remediate contaminants. The objective today is to highlight some of this technology. I won't go into great detail about the technology. I just want to touch base with a few points just to kind of give you an idea. And then if there's some interest, we can follow up with our engineers. So ultimately, I want to look at the sustainability concept with respect to incorporating technology. So looking at how we can better treat for water reuse, energy efficiency and reuse, and nutrient reuse and or elimination. And then the second component I want to touch base on is the contaminant issue and how we can better ourselves with respect to treating, whether it be our water and or wastewater, with respect to the contaminants that come into our plants, and those contaminants that fall into the category of the emerging contaminants. So some of these difficult to remediate compounds that can quite readily pass through a wastewater treatment facility. Sustainability as well as environmental and health benefits can be realized when we incorporate better water treatment technologies. Technology can be used to improve existing treatment facilities as well as support a decentralized system. The use of small, modular, decentralized treatment plants can enhance the water and wastewater treatment scheme. As water reuse, nutrient reuse, and energy reuse continue to grow, decentralized plants become more practical, as a centralized treatment is not always effective when considering resource recovery or reuse. For instance, the cost to install pipelines that carry recycled water from a centralized treatment plant to the point of use can far exceed the cost of building a satellite treatment facility. Today's technology can reduce the footprint required of a typical centralized treatment facility, as well as support the installation of smaller decentralized systems. The implementation of newer technology can have a positive impact on capital and operating costs. Wastewater can be treated to various qualities to satisfy demand from different sectors, including industry and agriculture. It can be used to maintain the environmental flow and can even be used for drinking water. Wastewater treatment for reuse is one solution to the world's water scarcity problem. Water reuse frees scarce freshwater resources for other uses or for preservation. So the two components that I want to talk about a little bit today with respect to water sustainability is one, how we treat the water with respect to the environment. So if we're assuming environmental discharge, we want to ensure that we're treating the water as best as we can to reduce the impact on the environment for which where the water will end up. And then the other aspect is the recycling component. So we're looking at water and treating it so we can reuse that water, and where and how we're going to reuse it. So whether it be for irrigation, back in for industry, or in fact for potable water use. Byproducts of wastewater treatment can become valuable for energy generation, making wastewater treatment plants more environmentally and financially sustainable. Incorporating technology can make our treatment plants more efficient, as well as improve energy capture. So looking at energy sustainability, there's some components that we want to focus on. One is the plant operation itself, to ensure we're running as efficiently as possible. So we want to incorporate the technology that'll improve efficiency, incorporate things like AI, renewable energy sources. We want to implement remote monitoring and control. And then, of course, we want to make sure that all involved are properly trained to operate the system as efficiently as possible. The other component with respect to energy sustainability is the generation or capture of the energy that's generated. So capturing, assuming it's methane coming off as the biogas, taking that methane and either putting it back into the system, the grid, so to speak, or reusing it on site. But the other component is capturing that methane to prevent the greenhouse gas emission aspect. So control it to prevent, like I say, the greenhouse gas emission itself. Byproducts of wastewater treatment include nutrients that can be used for agriculture and farming. Capturing these nutrients from wastewater treatment can improve a plant's ecological footprint and environmental impact, as well as improve a plant's financial sustainability. So looking at the nutrient component of our wastewater, there's two factors. One, we've got nutrients coming in that can easily be reused for agriculture or farming. So we want to capture those and reuse accordingly. But if we choose not to, we want to, at the very least, ensure that we've eliminated the nutrients or destroyed those nutrients. So we're not creating a negative impact on the environment when we discharge into our rivers, lakes, and oceans. As part of the sustainable treatment strategy, wastewater and water treatment practices should consider the difficult to remediate contaminants. This includes the reduction and removal of organic compounds that can have an adverse effect on the environment as well as our health. These contaminants are known threats for aquatic ecosystems and human health and are becoming a major issue for water utilities. These contaminants are sometimes referred to as emerging contaminants. Sources of these contaminants include pharmaceuticals, whether related to human or animal health, cosmetics and personal health care products, industry, farming and agriculture, building material and textiles, and leachate related to landfills. The next three slides will identify some examples of emerging contaminants. These are examples of difficult to remediate compounds that can pose an environmental and health threat. These compounds can pass through a wastewater treatment facility if provisions for the removal have not been made. The list I'm going to go through is not exhaustive. I've selected these simply because they've had some notoriety as of late. So we've seen some of these names in media, etc. So I thought I would just compile a few and kind of go through them. Consideration should be given to these as well as other emerging contaminants. So the first on our list is PFAS, the PFAS family anyway. The source is from firefighting foam, retardants, adhesives, and cosmetics. We're already seeing measurable amounts found in drinking water, and the PFAS can be linked to endocrine disruption, thyroid disease, cancer, and liver damage. Sulfolane is an industrial solvent. It's water soluble. Its effects are currently being studied. 1,4-dioxane is a solvent stabilizer used in personal health products and cosmetics. It's water soluble, resists biodegradation, and therefore has a bioaccumulation effect. It's known to be toxic with negative impacts to the nervous system, liver, and kidneys. Microplastics, of course, we've seen a lot about microplastics in the news recently related to personal care products and cosmetics. There's a concern for environmental accumulation. They are harmful to marine life and as well promote the transport of toxins if the microplastics are consumed. So through the ingestion process, toxins can be exposed. Siloxanes related to sealants, adhesives, coatings, plastics, cosmetics. There's a concern again with bioaccumulation, and these are toxic to marine life. PDDEs, building materials, textiles, and electronics, adhere to sediment and then therefore become a concern with respect to bioaccumulation. These can impact neurodevelopment and are as well known as a carcinogen. Triclosan is a popular antibacterial additive used in personal health products and cosmetics. There is some bioremediation, but for the most part, triclosan can pass through a wastewater treatment facility, and therefore we have an environmental discharge, and then of course bioaccumulation. The impact alters human regulation, creates antibiotic resistance, and is toxic to marine life. NP and NPEs used as detergents, emulsifiers, wetting agents in industrial or household products. Little bioremediation, therefore we can expect bioaccumulation as this compound passes through a wastewater treatment facility. Toxic to marine life, related to reproductive and developmental effects. EE2 synthetic hormone, bioactive estrogen connected to human health, livestock, and aquaculture. Little bioremediation, therefore environmental discharge, and of course bioaccumulation. This can interfere with sex determination and reproductive development. So again, just a small list that I compiled just to kind of run through. Like I say, it's not exhaustive, but these compounds and others are considered the emerging compounds. These contaminants are difficult to remediate and should be addressed during wastewater treatment. So we need to provide a process step that adequately deals with these emerging contaminants. Traditionally, a typical wastewater treatment facility focuses on reducing TSS, BOD, nutrients, and microbiological pathogens in order to safely discharge into the environment. The typical treatment plant is composed of a primary treatment followed by a secondary treatment. The primary treatment targets TSS, total suspended solids, whereas the secondary treatment targets BOD, COD, TOC, as well as nutrients, the ammonia and the phosphorus. Traditional plants do a good job at treating wastewater. However, when we view them through a sustainability lens and consider resource recovery, or consider the emerging contaminants, we can identify process steps where improvements can be made. The technological improvements or plant design can be considered based on recovery objective and contaminant type and or waste source. The type of technology used will depend on the plant design objective. For reuse, it's the what, where, and how versus the discharge, where and how. Ultimately, what isn't reused and therefore discharged should be of a quality that best protects the environment. So when we look at existing plants or we're looking to design a new plant, we want to consider our objectives with respect to nutrient recovery, energy recovery, and water recovery and design accordingly. But as well, we need to consider the contaminant type. What is the source of the waste, whether it be industrial, mining, domestic, or agriculture. Each can have a variance in the type of waste that ultimately makes its way to a plant, and therefore the treatment designed to specifically treat that type of waste or concentration of various species of contaminants, etc. Heavier loaded BOD, TSS, what have you. This is just an example, I guess, of a layout of a plant design stretched a little bit, where you can see there's some highlighting the water treatment component. So we could look at a plant like this and incorporate varying technologies to improve that component of the water recycling and how we would use it. As well, if you look at a plant design like this, you might break into some modular systems, one to handle the industry and do some pre-treatment before allowing the water into the main system to head to the centralized plant. Again, another plant design. This one design is slanted more towards the creation of biogas. So we've got some anaerobic digesters and therefore some biogas creation, methane in this case. So our plant and the technology we can incorporate can better assist with or be geared towards a better process with respect to methane development, capture, and reuse. The following are some technologies that can be incorporated into existing plants, and they're used to build smaller, modular, decentralized plants. These technologies can support our sustainability efforts, as well as improve the quality of any effluent that is discharged to the environment. It is possible to combine some of these technologies to further improve the water treatment process and/or improve any discharge. So some of these technologies have been available for many years. And again, I won't go into great detail about each, but simply wanted to touch base or touch on with a brief description. So if we're looking at wastewater treatment plants, and we're considering the primary and secondary treatment components, some membrane technologies can be incorporated. We can look at MBR, MBBR, and MABR. We can also look to DAF or SAF for some improvements. Chemicals, which we've been using for years, of course, but there's always improvements, and we look at the efficiency with respect to how we introduce our chemicals, etc. And then looking at the effluent side of things, or the effluent end of our water treatment, we can look at some technologies to better improve the effluent, polish it, if you will. We can look at some media technologies, activated carbon, ion exchange, modified media such as green sand or sulfur modified iron. We can also look to advanced oxidation processes, so AOPs. And finally, we can look to UV, all these helping with the final effluent quality. And then again, looking at how we plan to reuse or what we plan to do with that effluent. MBR, or membrane bioreactor, is essentially the combination of a membrane technology and activated sludge. The key difference between a conventional activated sludge process and a plant with MBR is footprint, or size of the overall system, and the quality of the effluent. MBR technology would typically be combined with the final sedimentation. So I've just pointed out in our secondary treatment, we go through aeration and then into a final sedimentation tank. This is where we can incorporate MBR technology. The use of a membrane barrier layer or to remove solids allows decoupling of a plant's hydraulic and solid retention time. So the HRT and the SRT are reduced. Unlike a conventional activated sludge treatment process that relies on sedimentation for solid separation, the MBR provides a definitive boundary layer that provides complete solid retention. Membranes used in MBR systems contain microscopic pores that are significantly smaller than many pathogens and microorganisms, meaning a high level of disinfection can be achieved with just an MBR. Both solids and pathogens are retained by the membrane, providing a highly disinfectant, low turbidity effluent. The combination of effluent quality, small footprint, and low life cycle costs make MBR a viable technology for today's reuse projects. So quickly seeing the benefits of incorporating the MBR, we'll see an improved BOD reduction, as well as TSS reduction. And of course, nutrient removal is also improved. The other component is MBR requires less working space, if you will. So the size of a plant treating the same amount of water can be reduced. And looking at this table, you can see some good numbers with respect to BOD removal, TSS removal, and the nutrients, etc. Turbidity for sure. A moving bed bioreactor, or MBBR, is defined as a biological process for treating wastewater with some unique characteristics that make it a beneficial alternative to traditional methods such as activated sludge or a tricking filter. The treatment capacity of existing wastewater treatment plants can be significantly enhanced simply by adding MBBR. The incorporation of MBBR promotes the use of smaller, modular, or decentralized facilities, which can reach significantly higher treatment efficiencies by using high-performance biofilm carriers. MBBR would be added in the aeration component in the secondary treatment. Some benefits for MBBR are the footprint, so we can maximize footprints or reduce the overall space required for treatment. Because of the maximized surface area leads to an MBBR aeration tank that can effectively treat the same amount of water as a much larger tank used in the traditional process. Simplicity. MBBR has the advantage of being simple. It allows nature to take its course, which minimizes the role of the operator. Low maintenance. System is largely self-moderating, so users can trust it to operate effectively without the need for demanding ongoing maintenance. And it's efficient. MBR systems can work much more quickly than conventional methods to treat the water. The hydraulic retention time, the HRT, for BOD and nitrogen removal with an MBR is around 3 to 4 hours. There's 4 components to an MBR system or MBBR system. You have the basin reactor. So the MBR process takes place in a reactor or an aeration tank. Influent enters this basin for treatment, a second basin for further MBR processing, or for another type of water treatment process can be used. You have the media itself, which is the heart of MBBR. So the basin is filled with thousands of these small plastic chips called media or carriers, and they occupy 50 to 70% of the tank. It's the chip design that maximizes the surface area. The chip itself, or the carrier, has the same density that of water, allowing the chips to mix throughout fluid rather than floating or sinking. The aeration component needs to take place. So you have a grid that introduces air into the system. And then finally, a sieve just prevents the movement of the carriers out of the basin of the reactor. So it acts like a filter. Effluent can move out, whereas the chips themselves stay in place in the reactor. Membrane aerated biofilm reactor, or MABR technology, provides an improvement to aerobic wastewater treatment due to its highly efficient nutrient removal and its energy efficiency. The MABR provides highly efficient biological nutrient removal, resulting in operational savings and minimal footprint requirements that make decentralized treatment more feasible, as well as improve existing centralized plants. The MABR process employs a gas-permeable membrane to deliver oxygen to a biofilm that is attached to the surface of the membrane. It has the added bonus of intensifying treatment capacity and improving performance by increasing the biomass inventory in a given reactor volume. MABR technology is based on passive aeration, that is the diffusion of oxygen through membranes. Small to medium capacity MABR systems save up to 90% on energy used for aeration compared to conventional plants. MABR's energy efficiency means it can be operated with alternative energy sources, and making it a great ideal candidate for decentralized units as well. So the main principle with MABR is the movement, and it's somewhat passive. It's not high pressure is not required. So air diffuses passively through or across a membrane where biofilm is attached and an aerobic zone is created. And as oxygen is depleted there, further to the outside of the membrane, an anaerobic zone is created. And so in essence, you get a full nitrification and denitrification process, all while utilizing less energy to move the air and introduce to the bioorganisms. Activated sludge treatment has long been used for aerobic wastewater treatment, but its aeration stage is particularly energy intensive and as a result expensive. Oxygen is typically pumped through diffusers to create bubbles, but most of the oxygen rises to the surface without being used, and valuable energy is wasted. The membrane aerated biofilm reactor enables the upgrade of conventional activated sludge plants for nutrient removal and capacity expansion in existing tank volumes, while significantly reducing the energy required for aeration. MABRs provide an energy efficient alternative that provides a very high quality effluent. So the MBBR would be incorporated again in the aeration stage of the secondary treatment. The huge benefit to MABR is the energy savings in that aspect with respect to introducing air to the microorganisms, because it doesn't require high pressures. Little energy is required to move that air into or introduce it to the microorganisms that grow on the membrane itself. So typical aeration through diffusion would be 70% of a plant's energy with only 10 to 15% transfer. That's with a typical plant, an aerating plant, and compare that to 85% of MABR. Utilizing MABR allows for a reduced footprint, increased treatment capacity, of course. And then by creating that anaerobic and aerobic zone, or aerobic to anaerobic zone, we see better nutrient removal, so nitrification and denitrification, as well as phosphorus removal. And overall, we see an improved effluent. Dissolved air flotation is a proven and effective physical chemical technology for treating a variety of wastewater streams. DAF systems are designed to remove total suspended solids, biochemical oxygen, and oils and grease from a wastewater stream. Contaminants are removed using a dissolved air and water solution produced by injecting air under pressure into a recycle stream of clarified DAF effluent. This recycled stream is then combined and mixed with incoming wastewater in an internal contact chamber where the dissolved air comes out of solution in the form of micron-sized bubbles that attach to the contaminants. The bubbles and contaminants rise to the surface and form a floating bed of material that is removed by a surface skimmer into an internal hopper for further handling. SAF varies slightly from DAF in the way air chemical are utilized. There is less emphasis utilizing SAF on the dissolving of air into the solution. Chemicals have long been used to support water treatment. Improvements can always be made, of course, and efficiencies improved. Chemicals are used for pH adjustment, precipitation, improved coagulation and flocculation, and oxidation. So therefore, chemicals are valuable in helping with nutrient removal, TSS-BOD reduction. As well, chemicals can be used for specific target contaminants. So we can target a specific organism or contaminant, with appropriate chemicals. An example being in the mining industry, we could look at sulfur dioxide to remove cyanide. That's a byproduct in the processing of gold. Of course, disinfection. So chemical being chlorine can be added to assist with the disinfection process. An interesting and perhaps improved approach to chemical addition for the purpose of coagulation and flocculation comes from biopollinate. Biopollinet's PNC formulation brings an all-natural product that can be adapted and modified to meet a specific need or application. So it's customizable. Biopollinet's BNC platform technology is a customizable approach to convert natural macromolecular biopolymers to strong coiled nanostructure network solutions. So biopollinants BNC technology can be used for dewatering, improving the dewatering of our sludge, tailings recovery, biogas nutrient recovery, as well as precious metal extraction. Benefits of biopollinates product is the optimum particulate size. So nanoparticles geometry very efficiently penetrates and encapsulates target particulate substrates. The biofunction action, simultaneous use of physical entanglement and chemical grafting to rapidly encapsulate and target substrates. The substitution rate normally can displace incumbent synthetic chemistries on a 1-to-1 basis or better. And of course, the green chemistry component, the product is all natural. So we are reducing or improving the biodegradability and not introducing harmful compounds, if you will, to the environment when we dispose of the sludge, if we dispose of the sludge and don't process further. Turning our attention to the effluent component of a wastewater treatment plant, I would like to start with a media. So the appropriately selected media technology can be an effective defense against the emerging contaminants, as well as other inorganic or organic contaminants. Medias or resins can also be used to target specific species of contaminants. So it's understanding again the waste and the effluent, we can incorporate a better media, if you will. We can choose and incorporate a better media, and there's many media types to choose from. The media technologies include activated carbon, so ion exchange and modified medias like green sand and sulfur modified iron. Medias themselves or resins can work through absorption, ion exchange process, as well as medias can provide oxidation and then provide a physical capture, so a filtering effect all in one. With that in mind, we know that medias can be effective in helping us with nutrient removal, TSS and VOD reduction, and as well, medias can be used to specifically target a contaminant. So a known contaminant can be extracted from the effluent. Effective as well, media can be used for the effective removal of emerging contaminants. Most environmental pollutants can be successfully eliminated or converted to non-toxic materials by one or more electrochemical processes, including electrochemical oxidation, electrochemical reduction, electrocoagulation, and electrocoagulation flotation, electrodialysis, and electrochemical advanced oxidation processes. From the viewpoint of high efficiency and low resource consumption, electrochemical technologies can be used either as a pre-treatment step to increase the biodegradability of a pollutant, or as an advanced treatment method further to reduce COD or color in the water to achieve a relevant effluent standard. So I put electrochemical in our effluent treatment component of this presentation, but in fact, electrochemical processes can put to the front of treatment. In some cases, only a minor amount of sedimentation removal is required before, so pre-treatment, if you will, before an electro treatment process can take place. Current Water Technologies out of Guelph, Ontario has designed and developed a proprietary electrochemical system built around its electrochemical reactor. The amyl system will break down ammonia into nitrogen without the generation of harmful byproducts or greenhouse gases. The amyl system can be further adapted with amyl H2 reactor to generate hydrogen gas that can be used as a fuel source. So the hydrogen can be used on site or sold into a grid. Just a quick layout of the phases of this technology, and again, provided by Current Water Technologies. So the key benefit here, of course, is the nutrient removal, in this case ammonia, and the byproducts that's created, kind of running straight to nitrogen gas and hydrogen. So the benefits, again, conversion of ammonia into environmentally friendly nitrogen gas, permits high H2 hydrogen production and high ammonia removal rate, compatible with renewable energy power resources, does not produce nitrate or the greenhouse gas N2O, achieves total ammonia concentrations less than 1 milligram per liter in treated water. Efficiency is not affected at low temperatures where biological systems are ineffective or can be effective or slowed down anyway. No fouling or biofilms or inorganic materials. Able to operate intermittently without startup delays, fully automated with low maintenance and remote monitoring. Boydell offers an electrochemical process that isn't necessarily limited to the effluent. Through a two-zone flow-through process, Boydell's electrochemical process can effectively treat raw wastewater with a minimal pre-treatment. Screening is all that's required. The two-zone process includes electrocoagulation and electrooxidation that leaves a sludge that is odor-free with 30% solids composition. The technology can be used to treat sludge from existing centralized plants with a cost saving of greater drying capacity. So a huge plus for Boydell's technology is the byproduct sludge, the dryness, if you will. So the water concentrates in 30% solids, which is an improvement from a typical 20% solid composition. And of course, the technology is effective at removing DODs, CODs, TSS, heavy metals, etc. Small footprint is a huge benefit as well. But again, just to reiterate, this technology can be used on the effluent end as well as on the front end. So it can accept raw water with minimal sedimentation treatment. So I think it's 1.3 millimeter sediment filtration is all that is required. AOPs are aqueous phase oxidation methods consisting of highly reactive species used in the oxidative destruction of target pollutant. AOP creates a more powerful and less selective secondary oxidant, the hydroxyl radical, in the water. This secondary oxidant can cause the oxidation of most organic compounds until they are fully mineralized as carbon dioxide in water. The hydroxyl reaction has a much higher oxidation potential than ozone or hydrogen peroxide and usually reacts at least 1 million times faster, thus leading to a smaller contact time and footprint. Current treatment practices in existing wastewater plants struggle to eliminate emerging contaminants and pollutant. AOPs, thanks to their high oxidation potential, have proved to be an efficient solution for the removal of persistent organics. So of all the work that BI Pure Water does, we do have, where I indicated that we choose the best technology when we build our systems. There is one proprietary piece of technology that we have, and that's Biofilm, which is an AOP process. It's an electrochemical process, and a hydroxyl radical is created, and it is effective like other AOP processes, which would utilize UV and ozone or UV and a peroxide. Our AOP process, like theirs, is effective at removing those emerging contaminants that we discussed. Are also effective in PFAS removal, and can be effective at removing PFAS, as well as aromatic or non-aromatic compounds. The plus to AOP technology versus media, for instance, is that AOP technology destroys the compound. So you're not left with a concentrate. With media, there's that circumstance where you can have a saturated media that needs to be dealt with. So it's trapped and removed, one of these emerging compounds, but then it's to be dealt with. So whether it goes to a landfill or taken for further processing, AOP destroys on site. AOPs are also effective at precipitating heavy metals. The bipreliminate advantage, we feel, versus other AOPs is the cost. So the capital costs and the operation costs are in our mind, better, and through our tests have proven to be substantial. UV has proven to be an effective method for the inactivation of microorganisms such as bacteria, viruses, molds, and pathogens without the use of chemicals. UV can also be used for the removal of organic and inorganic contaminants, including chlorine, ozone, and total organic carbon. UV technology can be used in place of chlorine disinfection. UV technology requires no storage, handling, or transportation of toxic corrosive chemicals. UV is effective at inactivating a wide range of microorganisms, including chlorine-tolerant pathogens. UV treatment can meet water reuse requirements in order to satisfy sustainability objectives. Of course, UV technology has been available for years and years. I make mention of UV, more highlighting UV with respect to the newer high output closed vessel, so high output, low energy closed vessel systems. These systems offer smaller footprint versus chlorine contact tanks or open channel UV that's currently in place at plants. There's an ease of maintenance associated to this type of UV. Low pressure loss, so moving water through the UV, there's lower pressure loss and lower energy consumption. And of course, by utilizing UV instead of or in place of chemicals, more than likely chlorine, we have that added benefit of not creating disinfecting byproducts. So we're eliminating that component that might discharge back in the environment. And of course, no pH correction is required when we utilize UV. We can anticipate the advancement of LED UV. LED UV exists, but is currently used only for low volume treatment, therefore not compatible with larger wastewater treatment plant volumes or water treatment plant volumes for that matter. So LED technology is in around the 2 gallon per minute flow rate, but we, let's say, eagerly anticipate further development of LED technologies so we can see or treat larger volumes of water. Of course, the benefit of LED will be the energy savings, so making energy consumption less, so we'll be more efficient. Up until now, I've mainly been focusing on the wastewater treatment plants. I want to touch base a little bit on water treatment side of things. This is a schematic of a typical water treatment plant in the distribution system. The big components with respect to a water treatment plant come from the source itself. So where is the source water and what are the specifics regarding physical characteristics, chemical characteristics of that source, and what treatment is required to bring the water into spec. And of course, the other aspect is contaminants that are harmful for human consumption and how we can ensure that they are removed and or treated. So we need to select the appropriate technologies to make our plants more efficient and remove the specific contaminants, etc., that are found in our source waters. For the most part, the same technologies used in wastewater treatment can be applied to water treatment. The focus with water treatment relates to efficiency improvement while minimizing any waste. Water treatment processes will also need to address the emerging contaminants, especially for recycling wastewater, as some of these emerging contaminants previously mentioned have already made their way into our water source. Any treatment process should also prevent the creation of harmful disinfectant byproducts. Therefore, the appropriate technology will be required to remove any precursors. So the newer technologies will fall into some of the same categories. Membrane technologies. There's some improvements with respect to the membrane material, if you will, ceramic versus titanium versus stainless. But a big component to the membrane technology will be with how we treat the backflush water. So membranes need to be periodically backflushed, cleaned in order to continuously operate or utilize them. We want to trap capture and reuse that water. It's a huge component. So in the end, we're making our system more efficient. So there will be some solid waste, of course, if any solids are removed in our process when they are removed. And then all liquid waste is recycled back into the system. So we don't see this discharge or loss of that water.
So Jeff, sorry to interrupt. We're just about at the end of our time here.
Oh, are we? Okay.
Do you want to take a couple of minutes and then we have a few questions? Do you want to
sure.
take a couple more minutes to wrap up and then we have a few questions in the chat line for you?
Great, I'm almost done. Anyway, that's perfect. Thanks very much.
Okay.
So quickly then, DAF and SAF can be used. Chemicals, of course, it's all about efficiency, and then looking to products from people like biopollinant, where we're using an all-natural product. Media technologies, again, specifically address certain contaminants. In this case, what the source water is, the characteristics of the source water. And AOPs, like mentioned, sadly, some of these emerging contaminants have made their way into our wastewater, so we want to ensure they are removed and destroyed. And then newer technology, electrostatic deionization, which is we can help with selectively reducing total dissolved solids. So it isn't an all or none. We can bring a water within spec without you consider RO, where it's pretty much a membrane that removes 95 to 99% of all total dissolved solids. ESD can be tweaked, and we don't necessarily need to, if we don't have to, reduce to that level. So again, wastewater treatment, it's more about efficiency improvements, incorporating AI for process optimization, remote monitoring and controls for process optimization, and of course training, and dealing with contaminants. Allergens becoming more of a factor with the demands that are stress is put on our water sources. Agents, arsenic being specific examples, and of course the emerging contaminants and the disinfectant byproducts. Yeah, so that's good for me for right now. If there are any questions, please feel free to ask.
So, Jeff, can you see the chat line?
Oh gosh, yeah. And, yeah.
So there's, I can either read the questions out to you or you could read them out loud and then answer them. I'm not sure what's easier for you.
So, we go all the way to the top, I guess?
Yeah. So there's a question about what is the sludge classified as, A or B, after the sludge bed? I think that's the first question.
Sludge A or B. I guess it depends on like specifically to the type of treatment we're putting into place, or in general with a typical waste plant. I might need a little more information sorry to answer the question.
Okay. And then I think there's another question shortly after that one that says, do you backwash the MBBR chips, or is the sludge pumped to a drying basin? Yeah,
you don't. So you don't need to backwash the chips. There is some sludge monitoring and control, but it isn't as intensive. That's the right word, as a typical activated sludge process. So for the most part, the chips, the carriers, they grow their media, and you don't have to intervene. There'll be just about a collection of sludge that might fall, that might accumulate in the tank, but it's not a matter of feeding and it's not a balancing system.
Okay, and I think there's one more question there about how does your, and I apologize for the acronyms, how does your AOP remove your PFAS?
So the biopreliminate, it'll be a destructive process. So it's an electrochemical. A hydroxyl is created. We've seen some preliminary tests have shown it to be effective at breaking down fast, or PFAS. Okay. So it's a full destruction. It isn't an entrapment or removal, and then moved to deal with it. It will effectively break down the PFAS. And it may break it. We're seeing, like say, effective breakdown where we measure for PFAS after, we're seeing lower numbers or signs of lower numbers. And then the byproduct may need to be treated, but can be treated biologically.
Okay, thank you. Kim, any last questions in there that I've missed? Sorry, we just have one more question, I think, that's come up. I can't read it, just a sec. Sorry. Okay, I'm interested to know more about the water treatment process as I treat for potable water only. How can I get the remainder of your presentation? Thank you.
Can you see, if you can see my email online here, fire me an email and I'm happy to share information with you, or if it doesn't become abundantly clear that my expertise is in deep waters, I'll connect yourself with an engineer and we can get the information you need for sure.
Okay, well, thank you so much for your presentation, Jeff. It was very interesting.
Okay, thank you.